Welcome back to Element 14 Presents. I'm Clem, and like any sensible deranged madman, I like breaking stuff with hydraulics. But the difference between fooling around and science is writing it down. So let's do some science. I have newly acquired for myself a hydraulic press, and I use this for material testing. So I really want to know, when does stuff break? This hydraulic press can exert a force of up to 20 tons, so I can break pretty much everything if I want to, and I also can use it to assemble press fit stuff, of course. But the main problem is, when do you know how much force is applied? Because hydraulics don't really give you a sensible readout. It either does the thing and breaks or it doesn't. So we're building a digital readout, and that also gives us serial data and stuff, for writing it down. Science. This is my hydraulic press. I recently acquired it, and basically what it does is you pump here, and then this bottle jack goes down and presses on stuff really, really hard. And there's no way to tell how hard that was. So we are going to have to measure the actual force that is applied here and display that in a convenient way so I can easily film, document, and measure how much force it takes to break stuff. So of course I could now draw up like custom PCBs and stuff like I did on many episodes, but I think this is a project that a lot of people could use at the home shop. So it should be done with like regular available stuff. So we're basically using modules. A display module, a load cell, a thing to read that load cell, so an ADC of some kind, and an Arduino board. And then we pack that up into a package and get it on the press. And because this is a 20-ton press, I need to get up to some reasonable forces. So we're using a 2-ton load cell, so I can at least measure forces in the 1 to 2 ton range. Because at 20 tons, I think I'm pretty much breaking the press itself anyway. Weight measurement or force measurement is basically the same thing. Weight is just the force that is applied to a body by gravity, and that's the force that puts it down. So it doesn't matter if you are measuring a weight that is pressing on a scale or the force that is pressing on a scale, it's basically the same. And kilogram as the unit instead of newtons, which is the actual unit of force, makes a lot more sense in practical terms when you just want to say, hey, you can put X amount of kilograms on there and it won't break. So I'm using kilograms for measuring force. I know it's technically wrong, but it's a bit more practical, and we do practical things here. And to get myself familiar with how this load cell thing works, I bought this. This is a weight measuring or a scale kit that you can get on Element 14. It has a pre-made module with an ADC, an analog digital converter, and a little microcontroller, and this cable that puts out the data over I2C, and a suitable load cell and these plastic parts. So basically you can put together a little scale, and that weighs in the 1 kilogram maximum region. So we can get individual grams on there. Pretty cool. And that is what I first tried to get myself familiar with how these load cells and stuff even work. So when you try to measure forces, you will get 2 terms pretty quickly, or actually 3 terms. First term is strain gauge, then there's load cell, and there's also analog to digital converter. So a strain gauge basically is a resistor of some kind that is applied to a piece of metal, and when that metal bends, the resistance changes, and you can measure that with an analog to digital converter, and that gives you an indication of how much that metal has bent, and you can basically calculate from that how much force has been applied to that piece of metal. But strain gauges are not that accurate, and the calibration is pretty difficult. So something that makes that a lot easier and more precise, especially if you want to measure a bigger thing that has maybe not evenly distributed weight over a bigger area, like a scale for humans does. You basically have 4 strain gauges in there, and they together form a wheatstone bridge, and that is also called a load cell. This kit here includes not just a strain gauge, it actually includes a load cell because it has more than one strain gauge on there. 2 on this side and 2 on this side, and together they form a wheatstone bridge. So this is actually a load cell, which gives us much more accurate outputs. Also, this little board has an extra microcontroller on it that allows us to directly calibrate it. Problem with that, I thought, hey, I'll just replace that load cell with a bigger one suitable for my project and then read that with an Arduino. But the problem is this calibration stuff is basically perfectly tuned for a load cell in the 1 kilo range, and I want one for 2 tons. So this is a 2-ton load cell. You mount it not like that, you mount it like this. So the part that is actually moving is inside here in this circular thing. There are 4 strain gauges in there forming a wheatstone bridge, aka a load cell, and then you have a cable to put that out. You basically get 4 cables on there, or 5 on this one. We have inputs plus and minus, then you have outputs plus and minus, and a ground wire for the case. What does it do? Basically, you put a voltage into it, let's say 5 volts, and for every increment of force this gets applied, a millivolt or 2 millivolts, depending on your load cell, is given back as a voltage. And then you basically need to amplify that voltage and read it with an analog to digital converter. And because that is not really trivial to get good measurements, there are special ICs that are not just pure analog to digital converters, they have amplification and they are basically meant to read load cells. And we use one of those, it's the same that's in the DF Robot kit, it's the HX711, which has a pretty ringing name, and that is very common. So you can get that, design a board around it, or use one of the pre-made modules. We're gonna attach this to this ADC, then read that in to an Arduino, and the Arduino should display it on a display.
Hi, I'm Derek, and this is DC to Daylight, where we explore the world of electronics in the realm of DC, audio frequencies, RF, and into the visible spectrum of light. Here we take electrical engineering topics out of the boring old textbook and bring them into life through demonstration and test. Sometimes we even build stuff, and if there's a way to test the concept at hand, we'll put it on a scope and measure it, and in doing so, hopefully bring it to daylight. So if that sounds like a good time to you, come hang out with me every couple weeks here at Element 14 Presents. Alright, see you there.
As my microcontroller, I use an Arduino Leonardo, and not just a regular one. I found on Element 14 a version that doesn't have the header pins soldered. And I thought, hey, if I find a display in form of a head that I want, I can basically solder them directly together, which makes it flatter and smaller. And since I will put this permanently in there, there's no point in having it detachable. So when I know this works, then I solder everything together. And guess what? I found a display, it's a DF Robot LCD shield. I haven't yet worked with an LCD of that kind, so that is also a good opportunity to get familiar with something else. And I specifically chose it because I read in reviews online that it's very good readable, because it's backlit and it has a pretty strong backlit that works great at 5 volts. With my microcontroller choice, the Arduino Leonardo, this is a ATmega32U4, this also means that it can be an HID device, which also means that I potentially could just connect my laptop and have it output the data over serial, not just via serial terminal, but I can also like make it type on the computer. So I just would open a file and let it type in while I'm measuring it, which could be pretty handy if I need to document graphs and data for destruction curves. The display we're using uses the UHGlib library. I have no idea why it's called that way, but that's a really handy library that supports a lot of displays, and since it's a graphical display, I can basically put on there what I want. So I make like force, and then I make a little bit of space for where I want the numbers to go, and then make kilogram at the end. So I always have a clear readout of what is measured. at any given moment. And at the same time, I wanted to put out that measurement and also the calibration values to the serial terminal, so in case anything with the calibration goes wrong, I can see what has gone wrong and know how to correct it. And yeah, we first need to assemble this thing, solder it all together, and then we have to think about calibration. Since we have put it together, we can now put it in a 3D printed and laser cut case. I had real struggles with that because it could be potentially so flat and small and nice, but at the same time I want it to be sturdy and easy producible. It just gave me a lot of headache, and instead of figuring out something super fancy, I just made a simple case, but I have put magnets on the back so I can stick it wherever I want. And now that we have that in, we also have a connector for the load cell, so it has a sturdy and safe connection to the rest of the device. We can power it via batteries or via USB if you just want to record directly on a laptop or just power it with a PSU. We now have to think about how it puts out that data and puts stuff on the display. So let's first check out the calibration, and then we'll see the actual code. The HX711 library needs a calibration value so it knows how to interpret the data that is coming from the load cell. And if you look under the examples in the Arduino IDE when you have installed that library, you will find a calibration example. Pretty easy to use. You start it by flashing it, open the terminal, send a T, which allows the device to start calibration. The load cell has to be at the 0 point, so no load is applied. Then it asks you to apply a load. In my case, because I have a 20-ton press and a 2-ton load cell, the bigger the weight that I put on there, the better it would be for calibration. So if I put on like 100 grams on there, that would be suitable for calibrating a 1 kilo load cell, but it doesn't make any dent for a 2-ton load cell. So I have weighed a motorcycle battery. This has pretty much exact 5 kilograms. So I use that as my calibration weight. Say this is what 5 kilogram is supposed to output. And then it gives me back a calibration value. And this calibration value is what we need to insert into the sketch. Quite a lot of code and some libraries I think I'm gonna use in future projects. Really like those. Let's put it all together, attach it to the press and break some stuff and see how much force it actually takes. In this video we have learned how to use displays, load cells and make a digital readout for press for science. And with the magnets I can just stick it anywhere I want and have my hands free for measuring science stuff while I break things. Let me know if you have any more ideas for equipment that you would need around your workshop. The best way to reach me is on the Element 14 community, and you can also go there to download all the files and code for this and many other projects. I gotta go, there's another project waiting for me.